Welcome to Oxpoon, the technology magazine. Hello everyone. Today I'm taking you on a journey through time, and I mean that in two senses. On the one hand, it has always been fascinating for people, especially artists and scientists, to retain a certain point in time for posterity. Just think of photographs. We capture a certain moment, a certain motif, and preserve it for the future, so to speak. And the other time travel that I mean is when we go about 200 years into the past. At the time, the Belgian physicist Joseph Plateau lived, and he invented the phenakistoscope. The device not only had a complicated name, but it essentially consisted of a disc. And you held this disc in front of your head, and stood in front of a mirror. And embedded in this disc, there were small, regularly spaced slits through which you could look and see what you could see in the mirror. The glass was also mounted in such a way that you could turn it, and small motifs were painted on the side facing the mirror. And when this disc turned, then you could see one motif after another. And these motifs, that was ultimately a sequence. It was like a cartoon. For example, a cat jumping over a chair. And if you consider that 200 years ago, when cinema or television were still unthinkable, then of course this was a minor sensation. It was real entertainment for people. And from this entertaining item, Simon Ritter von Stamfer came up with an idea and invented the stroboscope. So he basically developed this principle further. And thought, let's go into a dark room. There is an object in this dark room, and we emit flashes of light, short flashes of light. And if we imagine that what we are observing is, for example, an old grandfather clock with a large, long pendulum on it, which is always swinging back and forth, then with these flashes of light, when these are synchronized with the frequency of the pendulum, then it appears as if the pendulum is always at the same deflection, as if the pendulum is not moving at all, although we all know that it is moving. Or if we time it exactly so that it is at the bottom, we might even think that the clock is not moving at all. And this principle, and the way it works, was then developed further, which I would like to briefly demonstrate to you here using an example. I can simply let this wheel run, and then you can see that it's like a big Ferris wheel with the different colors here. And it's still relatively unspectacular. But I also have the option of moving this wheel forwards a little. And we can see here that we are between these spokes with this arrow, which marks a certain point down here. I have the opportunity to move exactly one spoke width forward, one spoke distance forward, or a little less or a little more to synchronize with it. We are now roughly in the middle. We do a little more, a few times. You see, we are approaching a spoke with the arrow. And if I do that again now, maybe again, now, we're pretty much exactly in the middle. And if I now go a little less far, so if I go exactly one spoke's distance further, then we're on the next one, and the next one, and the next one. And if we didn't have this Ferris wheel, but the wheel without colors, then in principle we would not be able to determine whether it is the same spoke at all, or if it is the next one, because they all look the same, because they have the same color. The fact that we can now observe this effect on television, where a vehicle is moving forwards but its wheels appear to be moving backwards or remain stationary, this effect has to do with the fact that our video cameras do not record continuously, but record a certain number of images per second. This used to be 24 or 25. Today, it is usually 50 images per second that are recorded. So that's 50 individual moments. In principle, you could now say that our camera is itself a kind of stroboscope because it only records certain moments per second. And that creates this effect, which I can illustrate again when I place this panel in front of it. And now I have to see that we have the arrow at the bottom of the picture. So we have this arrow here and the spoke behind it. And if I now move forward a little further than one spoke's distance, and I do that a few times in a row, then it looks, in reality, as if the wheel were turning backwards. In the same way, if I now move a little less than one spoke distance, then this effect is exactly reversed. And that's exactly what it is. What we can observe on television. And this is also exactly what we can analyze with stroboscopes in research or in industry. Do rollers run correctly? In the textile industry, for example, or in the printing industry, it is very, very important that rollers run smoothly. Now that I've demonstrated what the stroboscopic effect is, let's take a look at some devices. They used to be big and mechanical. Today they have become small, work with LEDs, and are very precise. They have become indispensable for applications like quality control in industry. I am holding the PCE LES 103 in my hand, a robust stroboscope or handheld tachometer, RPM counter. And as we can see, it really is suitable for use in rough environments. And when I switch on the device, we also see that the display is exceptionally easy to read, so you can still read it from all directions. And the display is also very clear. We can see the most important values immediately. The frequency of our strobe light. We have the duty cycle, the duration of the emission, and at the bottom we can even change the phase shift. Plus and minus, that's plus and minus, 359 degrees. And we are thus able, for example, to place rollers or other rotating devices in all possible positions. I would like to show you the device to demonstrate this. I have brought a fan with me here, and now I've already switched it on, but I wanted to show it when it's been switched off. So it has 4 blades, and there is a marking on one of these blades. We can see it here. But when I switch on the fan, then we see that we can no longer see anything. This marking seems to have disappeared. But now I can go on here with the strobe. And yes, as if by magic, this marking can be recognized again, so we can clearly see it in one place. And I can even change the frequency. Yes, we can see it even better now. If I go even higher, then we can see them in 2 places. So now we have approximately twice the frequency here compared to the fan. And if I go even further, then all 4 of them appear. Then we're at 4 times the frequency. Yes, and now the funfair mode is slowly emerging here, so to speak. So we can take another look at that here on the display. So now we're here. We were just at 16 Hertz. Now we're at 527 Hertz. I was able to set this very easily by pressing a key here. With this X2, I can double it. I can also fine-tune the frequency with the up and down keys. I can also change the units very quickly. But I can also change the individual digits in the same way. And also down here, I get to the area where I can change the phase shift and the duty cycle. So all in all, it's a device that I love because it's really very, very well thought out and is ideal for use in industrial plants. The PCE LES 103. Here, I am now holding the PCE LES 103, UV 365 in my hands. This is a very special stroboscope, because it doesn't work with conventional light. I can switch it on here. We saw it briefly in the display. It works with UV, with ultraviolet radiation. And this is very important in some systems. For example, when we observe rotating objects such as rollers that have seals with holograms. Then we can make these materials more clearly visible with this UV light. It comes, I can show it here at the front with 3 high-power LEDs. And when I switch them on, we can also see our camera, which can see the UV light much better than humans can. But I can also visualize the significance or the special nature of UV light using our Ferris wheel here. When I measure these colors, they are special UV colors that reflect particularly well under UV light. Then you can see that they really glow when I shine the UV light on it. This device is similar, even though it is not actually designed for this purpose. Similarly, if I hold the bill a little to the side, we can see the security features on the €50 bill here. But what it's actually intended for, we can look here at the little fan that I've brought with me. It has 4 blades, and only one of these blades is marked. When I switch on the fan, it takes a little while for it to start up. And then we don't actually see this marking anymore. It seems to have disappeared. However, with the stroboscope, with the frequency that I set here, I am still able to make the marking visible again. As if by magic, it appears here again. So we have set approximately 1 Hertz here. And if I double the frequency, then it appears twice, because 2 positions in 1 fan revolution are now visible at once. If I double it again, then twice 2 is 4. And so I can go on and on until we have our Ferris wheel here. Again, how it works, so I'll switch off the noisemaker here. The way this device works is very, very simple, very, very plain. You've noticed that I was able to double the frequency quite easily, or have it, as we see here. I can also fine-tune it, and I can also adjust it here. Adjust it individually using the digits. I can also go down here and change the duty cycle, which is the duration, the pulse duration, very easily. And at the lowest point, I have the option of changing the phase shift, plus minus 359 degrees, so that I can look at every position of the moving, rotating object in a simple, playful way, with the PCE LES 103 UV 365 for light within the range of 365 nanometers. This compact yet robust device that I am holding here is the PCE LES 103 UV 385. This means that it emits light at a frequency of 385 nanometers. This also means, as the name suggests, and when I switch it on, it is also briefly shown on the display. It is a device that emits UV radiation, which we as humans can only partially see. UV radiation means, for example, that if we take this wheel here, and there are special UV lamps, we can see how these colors really light up and reflect really well. We can see the same effect in our ID documents. And you can even see this from a distance. When I go over them with the lamp, other security features flash up that are only recognizable in UV light. So far, so good for stationary objects that don't move. Such a lamp is sufficient. But if we need to look at moving objects, for example security ink, then we need stroboscopes like the PCE LES 103 in this version for 385 nanometers. The device delivers 317 microwatts per square centimeter at a distance of 30 centimeters with the 3 high-performance LEDs that we see here in front, and has a resolution of 0.01 fpm, and is therefore suitable for a whole range of applications. To demonstrate the whole thing very briefly, I have a fan with 4 blades here, one of which is marked, and we see this mark as long as the fan is stationary. When I put it into operation, the marking disappears. But with the strobe, when I turn on the light, I'm able to make it visible again. So you can see the spot. And so too, if I then double and quadruple the frequency, then you can see that we ultimately pick out 2 or 4 positions, or even more. So these are the applications for which we need such a stroboscope for all areas where we have devices. In industry, rollers, for example, which are in motion, which we have to analyze, and which are sometimes equipped with UV holograms. I have brought you the PCE LES 400. This is a stroboscope for fixed installation and is used, for example, in research, in medicine, or for maintenance, for the repair of systems. And we can see that the device here has an easy-to-read display on which we can make the settings. We have a wheel at the top here, which we can use to make the rough settings. So that's what we see here, and for the fine settings, the keys are located here. We can also double or halve the frequencies. Using the key for the settings here, we have the option of selecting the phase shift between 0 and 359 degrees in a menu, as well as the FPM between 1 and 36,000. If we turn the device upside down, we can see below the 20 LEDs, which look pretty good, and I can activate them. You can see how bright this is. Our camera can no longer really capture and resolve it. And I want to show the device in action, and to do that, I have to turn it a little, in an unusual way, because I have a fan here, and this fan has a mark on one of the 4 blades that disappears as soon as I switch on the fan. But with the device, and now I have to switch on the LED here, I can use the device to make this marking visible again. And if I can find the right key on the back, if we double the frequency, we have the marking twice, of course. Or if we quadruple it, we see this marking a total of 4 times. Now I can switch the fan off again. It still makes a lot of noise. It's a top-class device with an external sensor, as we can see here, which means it has an external trigger input and can be controlled from outside. The PCE LES 400. Let's take another look at the 4 devices at a glance. Firstly, the PCE LES 103, a handheld stroboscope, a compact yet robust device that works in visible light. Very similar is the PCE LES 103 UV 365. It works with UV light within the range of 365 nanometers. And I have opened the menu for you here. As you can see, the duty cycle and phase shift can also be set very easily. Again, very similar. Another variant of the device shown above is the PCE LES 103 UV 385, with a frequency range around 385 nanometers. This means also UV light. And here too, I have opened another menu for demonstration purposes, where you can see that it also has a display-off function if you use it for a longer period of time. These devices work with a built-in rechargeable battery, so you can of course save a bit of energy and use them for longer on a long working day. In a completely different class, we have the PCE LES 103. PCE LES 103. This is a device not for mobile use, but for permanent installation in industry or research. It has an easy-to-read display, easy-to-use keys, an external trigger input, and above all, 20 extremely powerful LEDs that can be used to monitor just about any machine or device you can imagine. 4 excellent stroboscopes that I wanted to show you, and goodbye.
Discover and order the latest measuring and test equipment now on www.pce-instruments.com.